My name is Stephen Slaughter, and thank you for attending the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Matt Thomas and Jamie Kostelnick. For those of you who are new to this meeting, you can submit questions via the chat window or use the raise your hand feature in combination with your microphone and video camera. We'll wait until the end of the presentation to take questions. In the meantime, please keep your microphone muted. Today's speaker is Brittany Sealander, who earned her undergraduate in geology at UC Santa Cruz, followed by a master's in geology and geomorphology at San Jose State University, where she studied Sierra Nevada bedrock river incision. Brittany then worked as a lab and field tech at the USGS in Menlo Park, California, before starting a PhD at CU Boulder, where she studied hill slopes in Colorado's Front Range and the relationship to channel incision. Currently, Brittany is at the USGS, working as a Mendenhall Research Fellowship in the postfire debris flow project, where she is investigating the performance of the USGS debris flow likelihood model in places that have been previously untested. Brittany, thank you for being here today, and the virtual stage is yours.
Hi, everyone. Thank you for coming. My name again is Brittany Sealander, and the title of my talk is The Impacts of Wildfire on Debris Flow Hazards in Oregon's Western Cascade Range. And I'm really excited to share with you all what we're learning. This science was performed with our partners at Dogami, Nancy Calhoun and Bill Burns. These guys went out and did so much field work and were amazing resources. Let's start with some basics. What is a debris flow? A debris flow is a type of mass wasting, and mass wasting is simply just the movement of sediment down a slope under the force of gravity. And a debris flow is a type of mass wasting where a combination of loose soil, rock, organic matter, air, water mobilize as a slurry that flows quickly down a slope. Debris flows are commonly caused by intense surface water flow due to the heavy precipitation or rapid snowmelt. And that water erodes and mobilizes a lot of that loose sediment and other surface materials down steep slopes. And debris flow source areas are often associated with these steep channels. And the debris flow deposits are usually found as debris fans at the mouths of these channels. Oregon has a very rich history of debris flow activity. Dogami has published historical inventory of observed debris flows in their statewide landslide information database for Oregon called SLIDO. On the left, we can see these blue triangles pictured in this figure, and this is from their database, and it includes debris flows from over 150 years ago to, at least from this image, as late as 2014. And if we're looking at this image right here, we can see that a lot of those blue triangles, those historic debris flows, are concentrated in Western Oregon. Luckily, we have been studying a bit more about some of their hazard. A lot of what is known about debris flow hazard in Western Oregon has roots to this 1997-1998 El Nino event. And this was an event that was preceded by a wetter than average winter. So there was about 3 years in 96, 97, 98, where there was unusually high rainfall. And this was felt throughout the Western United States. And there was some widespread landsliding and debris flows that were triggered. The destruction left behind, particularly in Oregon, sparked an effort to better understand some of these regional or topographic conditions that would make some of these places more at risk for debris flow. The image to our left is this map that was developed, which is a threshold map for Western Oregon that provides estimates of these rainfall rates that would trigger debris flows. And this map was developed using paired inventories with regional rainfall data. And it's it's been serving as an effective preliminary warning system using these 24-hour rainfall intensities, where if rainfall intensities are above those specified, you are considered at risk of debris flow. The landslides and debris flow inventories that were used to create this map didn't include observations or caveats for burned landscapes. This could be problematic because wildfire increases the risk of debris flows. And I think this image does a pretty good job of explaining why. Here's a picture I took from the 2013 Rim Fire in Tuolumne, California. It was a pretty devastating fire at the time. And in this image, we can really see what happens. So wildfires simply burn off vegetation. In doing this, it removes all of the roots, the surface features, and that roughness that keeps sediment in place. And this decreases the surface soil cohesion. Burning off all that vegetation also can cause plants to release a waxy substance into the soil. And when that substance is released, the soils become kind of hydrophobic. And having hydrophobic soils will reduce soil infiltration capacity. So when you have the high intensity rainfall event, all of that looser, more easily eroded surface material can be more readily and more effectively become a debris flow. Here's another example from the 2016 fish fire in Los Angeles County, California. The USGS installed an automated rain-triggered camera to monitor post-wildfire debris flows. And this video is showing an intense rainstorm. In this video, you're seeing all of this soil, this rock, and water just flowing down very quickly down the steep channel as a slurry. And as you're watching this video, think about the amount of force and the potential hazard that this could pose to people downslope. The amount of force behind that boulder is not insignificant. While these post-fire hazards are heavily investigated in the tinderbox of the broader West, like California or Utah or Colorado, and the rest of the Intermountain West, the post-fire debris flow hazard in Oregon isn't and hasn't been as well studied. And that's because until recently, it hasn't been a massive problem. In 2020, though, that changed. We saw some major fires throughout the Western Cascade Range. This is a GIF from Dakota Smith's Twitter X handle from September 8th. And it shows the amount and the sheer size of everything that was burning. And these are the fires that are colloquially known as the Labor Day fires. And those are just fires that blew up on the 7th and 8th. And collectively, these guys burned over 1 million acres in a matter of days. These Labor Day fires displaced tens and thousands of Oregonians and killed 9 people. And additionally, a lot of those people who were displaced didn't have a home to come back to. These fires destroyed thousands of structures. Even as of a couple months ago, the health impacts from smoke inhalation and the economic impacts from the smoke and the buildings burned are still being grappled with. As of April, Pacific Corp is looking at $30 billion of new wildfire claims, with the federal government trying to recoup about $1 billion directly related to these fires. At the time, these 2020 fires were hailed as unprecedented or apocalyptic and once-in-a-lifetime events. But I think even our current environment right now with the fires that are burning in Eastern Oregon are showing that that's not the case. And the research that happened directly after these 2020 fires are showing that these types of burns, these very large, big, heavy hitters, are part of the typical fire regime that shaped the ecosystem here in Western Oregon. To the left, we have an image that is a simplified representation of the data that was presented by Riley and others in 2022 that shows where we have these moderately and high severity or moderate and high severity burns that are frequent to infrequent. We have been learning that as the planet is warming, we can expect the frequency of these type of once in a lifetime events to increase. Also interesting that I want to point out is that a lot of these places where we have these moderate, mixed severity and high severity burns overlap a lot with where we have the steepest slopes. So we know that there is potential for some pretty devastating post-fire debris flow hazards in Western Oregon. Luckily, the USGS has deployed the M1 post-fire debris flow likelihood model. And this model was published by Dennis Daly and others in 2017. And we can use this model to predict the rainfall intensity threshold that a specific basin when those rainfall intensities are exceeded, will likely have a debris flow. And they found that the short duration rainfall intensities are the best way to predict whether a burn basin will have a debris flow. So with this model, we just simply plug in terrain steepness, fire severity, and soil erodibility to be able to predict that specific channel's likelihood of a debris flow or that rainfall threshold that would trigger debris flow. This model was calibrated using data exclusively from Southern California. And you can see that by these little yellow triangles in the bottom left corner that are circled. And the reason that they use those specific data points were that this model or those data had the best debris flow timing and rainfall available at the time. But when that model was applied across the US through to those little yellow dots around the US, it performed pretty well and was applied across the broader West. The blue circles show locations where this model has also been applied, but with mixed results. Those orange stars over here, those are what we're looking at today, and where we also need a little bit more testing. As a recap, we know that Oregon has debris flows. We know that it has fires, and we have warning and hazard systems in place for rainfall intensity thresholds for debris flows that have been in unburned landscapes and for burned landscapes, but with that model only being tested in places that are kind of dissimilar to Oregon. Which leads us to our two primary research questions. First, how do wildfires influence debris flow hazard in Western Oregon? And second, how well does this post-fire likelihood model work in Western Oregon? To do this, we developed a pre-fire and post-fire debris flow inventory. That pre-fire inventory is done exclusively through aerial imagery mapping. And that post-fire inventory is done through a mix of both aerial imagery mapping and repeat field mapping. The aerial imagery mapping was performed in those blue polygons. You can see at the bottom of the screen, or in the inset, covers a pretty large geographic area in Oregon. The repeat field mapping was done in the 5 mega fires that burned in the 2020 Labor Day fires. So we used Oregon's statewide imagery programs database for our aerial imagery called OSIP. OSIP partnered with the National Agriculture Imagery Program, NAEP, to acquire and distribute some high resolution imagery from 1995 through 2022. There are imagery available from 4 to 5 year intervals between 1995 and 2018, and 2-year intervals from 2018 through 2022. And we map debris flows in each of those intervals for all of our available sites within those blue polygons. And we were able to constrain timing of those debris flows just to the those chunks of time that we have for our aerial imagery data. And we were also able to infer initiation mechanisms. And we inferred initiation mechanisms in a pretty fun way through the imagery. And we noticed 4 different types of initiation types. First, we saw a ton of shallow landslide initiated debris flows, and you could tell those were shallow landslides or initiated where that debris flow channel was completely excavated. You can see that, yes, that's our debris flow channel, but it had some type of landslide on it. In this example, this landslide is at the channel head, and that's depicted by, you can see it a little bit here, by a yellow triangle and a headscarp that's outlined in that U. Those landslides weren't always on the channel head, but they could be distributed throughout there that just continued as debris flow. We also saw not a bunch, but some deep landslide initiated debris flows, and those were identified pretty similarly to the shallow landslide initiated debris flows. They were just bigger and deeper, and those bigger, deeper landslides continued on as a debris flow. Another type of debris flow we noted were these runoff initiated debris flows. And these were identified by having these source areas where you could see a bunch of surface erosion that coalesced into a channel. And that channel was also excavated, looked like it had been cleared out through the debris flow. But the key feature was that sort of cone coming into that channel. Another fun one that we saw were these in-channel initiated debris flows. These were identified by just having that debris flow channel. And these ones we said were in-channel failures because they didn't have any evidence of deep landsliding, shallow landsliding, or distributed runoff and erosion. I should note that for the distributed runoff and erosion type landslides, the resolution for the imagery wasn't clear enough to see rilling, but you can tell it's there. So again, we also did repeat field mapping. And this was done in the Archie Creek, Holiday Farm, Beachie Creek, Lionshead, and Riverside fires. And the way we did this is we would drive through each of these, and by we, I mean Bill and Nancy. Bill and Nancy would drive through these fire perimeters and look for evidence of debris flows. So as they were driving through these massive fires, they would look for something like this, and they would mark, hey, there was debris flow. Or they would be looking for something a little less obvious, like this. And they would mark the lat long on it and whether there was a debris flow. As they were driving through, they would also note locations where there was no debris flow in the channels. So we ended up with a series of observations through time with channels that had debris flows or didn't have debris flows. We also added rainfall data to these field map observations. And this was done by looking for rain gauges within 10 kilometers of an observation. So we went and tried to find every single rain gauge we could within the fire area or around the fire area that we could tie to some of these observations. And we calculated the peak 15-minute rainfall intensity, which was important for the post-fire debris flows, and the 24-hour rainfall intensities for each observation point. In Oregon, Oregon's kind of wet, so we wouldn't just have one storm in between observation or periods of observation, and there would be a lot. So if we couldn't identify the exact storm that was triggering these debris flows, we would record the peak intensity for both the 15-minute and the 24-hour. And we repeated this process for every field visit. For those post-fire observations, we would also calculate the M1 model predicted rainfall threshold for both the observed and the observed debris flows and the observed not debris flows. And with that data, we would look at the rainfall peak intensities during that period of record and between field visits and see if we had any rainfall intensities that exceeded that M1 model predicted threshold. If there were rainfall intensities that exceeded that threshold, we would say that the M1 model predicted a debris flow would occur. If there was no rainfall that exceeded that threshold, we would say that no debris flow was predicted. And this was done for every single field observed point that we drove through. Now that we have our inventory, we can look at how some of our research questions, or we can begin to answer our two research questions. That first research question is, how does fire influence debris flows in Western Oregon? And it does so in two major ways. The first way is it changes the frequency. So if you remember back to that image of those blue squares, within those blue squares of our field site for our imagery analysis, there was about 29 debris flows per year in those 25, 30 years prior to it burning. After you burn it, that changes to 79 debris flows per year. That's massive. That's so many more debris flows. It's 50 debris flows more, 2.5 times debris flows from the background rate. Another interesting change is that fire changes the distribution of debris flow initiation types. So in this chart, where I'm showing you on the left-hand side, the distribution of unburned debris flow initiation types. And on the right-hand side, I'm showing you the burned distribution. From this figure already, you can see that distributed runoff and erosion initiated debris flows account for very little of the unburned landscape. But after you burn it, that pumps up to 24%. And shallow landslide, which was 69%, jumps down to 49%. Despite that 20% decrease in shallow landsliding, it still is the main initiation mechanism that's behind most of the debris flows we're looking at here. In-channel failures don't really change much, or don't really change between burned and unburned, and we didn't see any deep landslides initiated debris flows post-fire. I'm going to say that with a caveat of there were some debris flows that occurred within existing deep landslide complexes, but it wasn't the deep landslide that failed and continued on as a debris flow. This is a lot different than what we're seeing in a lot of other places post-fire throughout the Intermountain West. In Southern California, where this M1 model was calibrated and designed to predict debris flows, those were all initiated by distributed runoff. You can see by the orange pie that it's very, very different to what we see here in Oregon. So what does that mean as far as the efficacy of our M1 model? So this is our second research question, which is how well does this M1 model work? And this table shows the threat scores of the model performance in various regions. The threat score is the traditional performance metric that has been used to evaluate how well the model is performing. And the threat score is just something that describes the fraction of correctly predicted debris flows out of all of the correctly or incorrectly identified debris flows. Ideally, a 0 would mean that the debris flow model is perfectly and imperfectly predicting debris flow, so it's wrong every time. And a score of 1 means that the model is working perfectly every time. Nature is messy, so I put the original model threat scores up as the goalpost of what we're trying to aim for. The training data is the data that was used to calibrate the model, and that clocked a score of 0.42. And the test was 0.39. And the way to think about that is that we want to have scores that are as close to that as possible. I threw in the recent Central California performance, just to give you guys an idea of what it should look like. And this is a place where it performed pretty well. And this was in Matt Thomas's recent work from Central California. We see that Oregon has a threat score of 0.09, and that's a lot lower than other places where this has worked. And we touched a little bit about why it wouldn't work so well here. And the M1 model predicts, or we can use the M1 model to predict the rainfall thresholds likely to initiate a debris flow for a specific channel. And again, those debris flows were for those distributed runoff and erosion initiated debris flows. And we have learned that in Western Oregon, post-fire debris flows are initiating a lot differently than those in Southern California and the rest of the Intermountain West we've studied so far. So applying this model might not be the best call. And this is because debris flows initiated by water runoff are more likely to initiate from short duration, high intensity rainfall. And you don't really need a wet soil to begin with. You can dry out after the fire for as long as you want and then be hit with a massive high intensity short duration storm and trigger debris flow. This is a little different than those initiated by landsliding, where a debris flow is going to be more likely to occur after from more of a long duration, moderate intensity rainfall event. And for that landslide to be triggered into a debris flow, you need wet antecedent soil moisture. You need that soil to stay wet for long enough. So I'm going to take a deeper dive into the rainfall here. Here I present a figure of rainfall data with the 15-minute rainfall rates and the 24-hour rainfall rates for 3 different gauges in locations where we know exactly which storms triggered 7 debris flow observations. The Holiday 1 rain gauges are located within the Holiday Farm Fire perimeter, and the Oregon 4 rain gauges are rain gauge, and the D7 564 rain gauges are located within the Riverside burn perimeter. On the top 2 rows, we have the Holiday 1 and the Oregon 4 rain gauges showing rainfall data observation, showing the rainfall for debris flow observations that were triggered by some atmospheric river that started around January 12th in 2020, which was the first water year following the Labor Day fires. The bottom row, the D7 564 rain gauge, shows rainfall data tied to that debris flow observations that were triggered by a January 3rd storm in the second year following the 2020 fires. In each plot, there's a peak rainfall rate for each storm for that period of record, either in red or green, or I'm sorry, red or yellow. The red is the 15-minute rainfall rates, and the 24, or the yellow is the 24 rainfall rates. And it also shows, or all the plots show a cumulative rainfall recorded by the gauge for that period of record. That's in light blue. Each gauge is going to have the same light blue background for the cumulative rainfall. Each plot also has the peak intensity of the debris flow triggering storm, and that's marked by the black X on top of the storm peak rainfall rate line. And above that X, you'll see a date, time, and rainfall intensity for that triggered storm. So the 15-minute peak rainfall intensity and the 24-hour rainfall measurement is measured in millimeters per hour. And for the 15-minute, it reflects the highest rate of rainfall observed over any 15-minute interval, and it's extrapolated into an hourly rate. So that means if during a 15-minute period, 5 millimeters of rain falls, the peak intensity would be that 15 millimeters divided by 15 minutes times 60. So you would get a 20 millimeter per hour rate. And this metric is very useful and crucial for assessing risk associated with those short, heavy downpours of rainfall. So those, usually those distributed runoff and erosion debris flows. In contrast, those 24-hour rainfall measurements are the average of rainfall over a full day. And it gives you a broader picture of daily precipitation. And that 15-minute can tell us how those, how peaky and insane those heavy downpours were. The 24-hour rate can give us a little bit more insight into the daily rainfall patterns and give us context clues for some widespread flooding or maybe those landslide generated debris flows.
Ready?
So those 15-minute intensity plots have some different features than the 24-hour plots that I'm going to narrow in on. So this is the example for the Holiday Farm fire. The rainfall chart, in this rainfall chart, we can see there is that red dashed line, and that is the calculated M1 model threshold for each of the debris flows observed within the 10-kilometer radius of that Holiday 1 gauge. The M1 model predicts that debris flows would be likely for those two observation points once rainfall is above that line. So in this example, we have an in-channel failure and a runoff and erosion-initiated debris flow. And there would be two lines, but the threshold's pretty similar, so they just mapped on top of each other. For our 24-hour rainfall chart, it differs in slightly with regard to that threshold line. That rainfall threshold shown here is the minimum value for the range that was presented by that Western Oregon preliminary warning map. And the map has coarser resolution than our M1 model. So there's only one line shown. So, but for this one, it's that debris flows may happen. All right, so now that we're cleared up a little bit on what data is in this plot, let's look at some of the story that it's trying to tell. So the first thing that we notice right off the bat is that these high intensity early season rainstorms did not trigger debris flows. These black boxes in the holiday farm gauge show like four pretty high intensity storms that happened early on in the season that a debris flow didn't occur at. And this is reflected again in Riverside's rain gauge 4, where we have a high intensity event that didn't trigger anything. And in that 24-hour plot, we see the same thing, that we have this massive event that puts that vertical line in that cumulative rainfall plot and no debris flows. And in the D7 rain gauge plot, we can see that the first 2 years, we have some pretty high intensity rainstorms that don't trigger debris flows in the first 2 years. What else is this plot showing? In addition to the early season storms, we see that the short duration, high intensity summer events aren't triggering anything as well. In the holiday 1 gauge, that summer storm, I believe, was the highest intensity event that happened over the period of record. But when we went out, when Bill and Nancy went out, they didn't see any evidence of debris flows happening in those 2 areas following those really high intensity summer storms. And I'm going to belabor this point a little bit. In this chart, we have two examples of runoff generated debris flows, and those look most similar to like those we see in Southern California and throughout the Intermountain West. But in Holiday 1, we can see that this January 12th storm it's only 7.7 millimeters per hour compared to the estimated triggering intensity, which is 16.8 millimeters per hour. So it's being triggered by a very low intensity storm. With the Oregon rain gauge 4, we can see that there was a storm that exceeded that threshold, but didn't trigger a debris flow. And it wasn't until much later on in the season, January 12th, where we have a debris flow. We are seeing that debris flow triggering storms are caused by these more moderate intensity rainstorms that happen after several months of back-to-back consecutive storm events that are occurring over months. And from all of this rainfall data, we can see that maybe threshold alone isn't the most appropriate way to predict hazards in Oregon. And this is significant because this is how we're doing it right now in Oregon. This is how even with our unburned data set, our unburned map and our burned map. All right, so in conclusion, we have learned with these 2 inventories that wildfires affect the frequency and initiation mechanisms of debris flows. That before debris flows, you're going to have a lower frequency compared to after you burn them, and that the distributed runoff and erosion initiated debris flows are going to increase post-fire, but landslide initiated debris flows and in-channel failure initiated debris flows are still going to be the most common. And we also learned that rainfall intensity alone is not the best predictor of debris flow initiation in Western Oregon. That's all I have prepared for today. Here is my works cited page, if you're interested in learning more. This science was created with so many collaborators. Bill Burns and Nancy Calhoun are massive forces in this. And our collaborators, Josh Rohrer, Kevin Moffett, Annette Patton, Dylan Quinn, and Matt Thomas, all helped wrangle these rain gauge. Yes. But yeah, that's all I have. Are there any questions?